thanks everybody for coming. Maybe a little bit about myself first. I am more of a math geek than a programmer. R is really the first language I've really ever used to any extent. So I am not a programmer. I've been learning and using R for approximately 2.5 years. And I spend probably 6 to 8 hours a week either using or reading about or understanding R and data science. I was actually, as I was just going to say, recently competed for prize money for the first time in the Porto Seguro Challenge. The best score that I got was probably about 2/3 of the way down the leaderboard. But I got to, I think the last leading score I saw was 291. I'm not sure if I got any higher than that. I ended up at like 272, something like that. So anyhow, R and data science for me is more of a hobby than a job. I don't do any of this stuff on the job. So I really undertook this exercise back in the summertime over the course of several months, strictly for learning purposes. So anyhow, that's a little bit about me. So about the NFL draft. So for those of you that are football fans, pro football fans, I know that there are fewer and fewer here in Cleveland. The NFL draft is conducted in late April every year. That's kind of the best day of the year for the Browns. They select each year, 256 players are selected in the draft, which is 7 rounds times 32 teams, plus there are 32 compensatory picks. I'm not certain exactly how those are awarded, but I didn't even know that until I really got into this. But anyhow, there's 256 players a year. So I took on 2 challenges. For those of you that ever watch ESPN or pay attention to the draft, they always talk about the quarterbacks being at the top of the draft. So I was really trying to understand whether, first of all, whether there's a bias in the draft toward any particular player position, whether or not quarterbacks in general get selected higher in the draft toward others. Just curiosity. So is there a statistically significant difference between quarterbacks or any other position for that matter to be drafted earlier in the order than other positions? So that was one thing I took on. And the second one was to try to beat Mel Kiper Jr. and Todd McShay, who are on ESPN and the NFL Network. They're draft analysts in predicting where college players will be selected in the draft. So, again, just for fun, just wanted to see if how well I could do in this exercise. So, the data that I used was all the data from the NFL drafts for the last 4 years. So that's roughly 1,000 picks. Not a huge data set. And what I used for the predictors were for each of the draft prospects, their season stats from their final year of NCAA football participation. So they may have been juniors, they may have been seniors. As well as their NCAA combine statistics for the given year that they went to the draft. And then I actually created something separate called an off-the-field issue indicator, which would be appropriate for somebody like Johnny Manziel or a number of others. So I created that just to see how well it would work in the model. And the result that I was really trying to map to was what position would the player be selected in the draft, 1 through 256. So what were the challenges with this? One challenge is really need a different algorithm by player position. It's not the same algorithm for every position. So, for example, one of the things that they measure in the NFL Combine are the number of reps that you can do 225-pound weight lift. Well, I didn't use that one for the position that I was working on, which was the 2 positions that I worked with, which was quarterback and wide receiver, but that would be more appropriate for somebody that would be a lineman. And the other challenge was really, once you break it down to an individual position, you really have a limited data set. So there were 135 wide receivers selected over a 4-year period. So very small test and training set to use in trying to come up with an algorithm. So how was I trying to do this? The measurement that I picked was called root mean squared error for any given position analyzed. So what that is essentially it's the average difference between where the model determined that player should be picked versus where they were actually picked, number 256. So for example, an average or a root mean squared error of 3,600 means that the average difference would be 60, the square root of 3,600, 60 between the spot that the player was actually picked and where the model chose they would be picked. Make sense? And then I generally used, I didn't do this for every different model that I tried, but generally used 5-fold cross-validation to come up with the root mean squared error. So let's move forward. All right, one more slide before I actually get into the code. So I tried a broad array of machine learning packages in my analysis, and it was mostly based off of models that I have learned something about over the course of time. Most of them are traditionally used for regression type of analysis as opposed to classification. I did try a few that are traditionally used for classification. They didn't perform very well, as you'll see. So I think in 1 or 2 cases, I built an ensemble model. At the time that I did all this, I really didn't know the Carrot package very well. I've actually spent probably the last 4 weeks or so really spending a lot of time learning Carrot, which is a lifesaver, quite frankly. I really didn't know much about Carrot before. So, having said all that, let me actually go into here. Go into the code. I realize this may be a little bit difficult to read. So I'm just going to go to the important parts of this, or the things that are noteworthy. This is really just importing the data, grouping the data by position, and then this is a box plot of NFL draft picks by position between 2014 and 2017. So again, this was the first thing that I was trying to figure out was, are quarterbacks actually favored versus other positions in the draft, or any other position? As you can see, well, maybe you can't see, the third one here is quarterback, and they're actually selected on average later in the draft than either cornerback or defensive end. And to answer the question of, actually before I keep going, some of these other positions way over here, what you don't notice without seeing the data a lot, some of these last 4 positions, defensive back, offensive lineman, fullback, kicker, especially these 2 positions, when you look at the data, what you actually see is you've got actually defensive back, a safety is a defensive back, and a cornerback is a defensive back. When you get later on in the rounds of the draft, they generalize more, and you see players picked as a defensive back where they may end up being a safety, they may end up being a cornerback. OL, offensive lineman, is actually a guard, and where's offensive tackle? A guard and a tackle. Offensive, this is more of a generalization of those 2 positions. Then you've got fullback and kicker, and there weren't that many players selected for those positions. So if I keep going, this is where I started to get into some statistical analysis in order to determine whether or not there's a statistically significant difference between those different positions and where the players were picked in the draft. At the end of the day, here's what I'm looking for. At the end of the day, I was not able to prove at a 5% significance level. My significance level was 7%. I couldn't quite get to a 5% significance level that there were really true differences between the top 13 of these positions. So basically in that statistically significant or lack of statistically significant finding excluded these last four. It included everything from defensive end to tight end. And there's a little bit more behind that. Down here, this is what they call a confidence level interval, and essentially each line on this plot plots one position against another one of those positions, and in every case, every single line crosses the 0 point, which means essentially, again, not a statistically significant difference between any of the positions. So that was goal number one. So at the end of the day, my conclusion in summary, there is no proof of statistically significant difference between the mean pick level for the 13 player positions tested. So that was the first part that I went through. That was the first goal. So then it got a little bit tougher. Then really what I was trying to do, again, trying to get to the point of beating Mel Kiper Jr. So the goal then was to select the model that select the best model that predicts where a player will be selected in the annual NFL draft. Let's go down here. This is all just importing the data. Combining data. Let's see. Adding another, right here I was adding another attribute, which is the conference of the school. Down here, this NFL draft, this split command essentially took all the data and then it broke it up by position. So that took my 1,000 or so records down to about 130 records. Then we actually move into what I started doing with the wide receiver data. So at this point, again, I'm doing some more manipulation of the data, identifying missing data, and then imputing some of the values. So actually, let's go back. Let's go back for just a minute. Where was it that I was eliminating? Yeah, I can't tell. I'll probably come to it yet. Yeah, all right, back up here. This is where I was actually eliminating some of the fields that really didn't make any sense for the wide receiver position. So again, for those of you that have heard of the NFL draft, perhaps you've heard of the Wonderlic Test. The Wonderlic Test is one of the tests that's used essentially for quarterbacks, and I don't know much about it, but anyhow, it's really only applicable to that position, and was missing values for the vast majority of the records that I had. I also eliminated, like I said, the bench press type of measurements and so forth.
So you're saying the wide receivers still take the test, but you eliminated it?
There were a handful. It was like out of the 130 records, it may have been 5 or 10 of them that actually had a value. Yeah. So now I wanted to impute some of the measurements. So actually at this point, I only had 2 fields where I had to impute some values. And in these cases, I didn't have a lot of values to impute. So I basically took a fairly simple model, and for the vertical leap, it was essentially worked off of a model that equated, or I should say, there was a significant relationship between the 40-yard time and the vertical leap time for those players. So essentially what I did was where I was missing a value for the vertical leap time, I imputed it based off of a linear model that worked off of the 40-yard time. And that's what I was doing here. Same goes for the broad jump measurements. Again, if I recall correctly, I might have had 7 or so missing values for broad jump. And again, the best model that I was able to build, a simple model to impute those values, was again based off of the player's 40-yard time. So I imputed those values. Then once I had a full data set, then I did some transformation. So for those of you that are familiar with Carrot, there's a term pre-processing. So I pre-process the data, and I essentially, for many of the numeric values, I basically place them on a normal curve with the center being 0. And I guess I wasn't doing that yet here. This is just a summary of the data before I begin to actually begin to apply any model. So you can see some of the fields that I used. Just you can see the pick here, the college, the conference, the age of the player, whether this is the other issues indicator over here, height, weight, 40-yard time, vertical leap, broad jump, receiving games, receiving yards, receiving touchdowns, rushing attempts, and so on and so forth. This is where, okay, so this is actually where I z-scored each of the numeric variables. And then I had to transform 2 of the fields into factors. So the conference, essentially the conference field of what I was looking for was if a team is part of a Power 5 conference, Big Ten, ACC, SEC, and so forth, did that make a difference? Was that a factor in the model as to where the players were picked? So I started out with a simple one, which is ordinary least squares. And I used, at that point, I used a package called the Leaps package. And this is what you see here if you're not familiar with this. Essentially, you can't see all this on one screen, but starting here and moving down the next several rows, these are the different attributes that were used. Essentially, if the way that this reads is if you used a simple one variable model, you would see a star in for that particular attribute. I don't see it yet. It's got to be, oh, here it is right down here, receiving yards. So if it was a one variable model, it would use receiving yards. If it were a 2 variable model, it would use receiving yards and something, receiving yards and conference. And then if it were a 10 variable model, it would select 10 of these. So let's keep going. So at the end of the day, with respect to a straight ordinary least squares model, what I was trying to, adjusted R squared. Actually, in this case, I was using adjusted R squared in order to come up with the best model, and this R picked a 10 variable model. And using a 10 variable model, sorry, that's a different, which max? Sorry, I got to read back through my code. If I run a 5-fold cross-validation to see how many variables to use, then I end up with something closer to a 7 variable model, or 7 variables. And so what it ultimately selected were these attributes, what conference they were in, whether or not they had other issues off the field, weight, 40-yard time, receiving games, receiving yards, receiving rushing attempts for a receiver. And a 7-variable model provided me with a root mean squared error of 4280, which is essentially going back to my my example earlier. That's a difference of about 65 between where the model figured the player would be picked and where they were actually picked. That was my first attempt. You have a question?
So it's like a give or take of 2 rounds?
Yeah. Yep. That's right.
Did you transform the rank data?
Did I what?
Did you transform the rank data?
The rank?
Rank 1, 2, 3, 4.
No, I did not. I did not. From there, I then tried to use a ridge regression model. And in this case, this is where we're going to start to get into looking at many different models. I used a ridge regression model, and I came up with a value of 5157, which was somewhat significantly worse than the 4280. I then moved over to a lasso model, and I've got a handful of pretty charts in here. And in this case, the ridge regression model the lasso model gave me a mean squared error of 4718, which is still not as good as the straight out of the gate ordinary least squares model. Then I moved into a few things a little bit more complex. So I moved on into principal components and tried using a principal components fit. And we get down to a, 12? I think I ended up with, 12 principal components yielded a mean squared error of 64.28, which was right around real close to where I had ended with ordinary least squares. Then I moved on to a partial least squares model. Again, I'm just trying out different models to see what works. And with, where is it? Again, I ended up right in about the same place. I ended up with a mean squared error of 65.02. However, in this case, it was a much simpler model than with principal components in that it was only 2 to 3 components versus 12 using principal components. Then I moved on to try to, I ended up trying some tree-based methods. Now these are ordinarily used more for classification than regression, but I decided to give them a shot anyhow. And they didn't work out very well. So the first one, let's see, I was using the tree package, and I came up in that case with 10,251, or over a difference of over 100. So that was the best I could come up with using a straight tree package. Then I used random forest, and I actually got somewhat significantly better, but still not as good as my original partial least squares and ordinary least squares model. And I ended up with 5,938. Still, again, significantly higher than what I had with using the other models. Now the next thing I tried with gradient, I tried a gradient descent model. I will note, I know some of you are familiar with XGBoost. At this point in time, I did not know the XGBoost package. So I never tried the XGBoost package. I ended up using the gradient descent model. Whoops. And it came back, again, not a very good model, almost 10,000 again for root mean square error. Now I'm moving into an ensemble model. This is where I really didn't know what I was doing using Caret. Actually, I was using partial least squares. using caret. And in this case, I came up again with a root mean squared error right around the same values as I came up with earlier using PLS, of about a root mean squared error of about 66, 65. Then from there, I tried to move to a couple of advanced models that I really only at that point used once or twice. I tried neural network. So there's two different neural network models that I ended up using. Where is the, okay, so here's the library was NeuralNet, and again, it did not perform very well, about 10,800 again as root mean squared error. My understanding that I have learned since then is that these types of packages are probably better for image recognition than they are for regression, learning to me. But anyhow, I tried them out. I then moved to another neural network model called NNet, which was ended up giving me something better, but again, still fairly far off from the principal components values that and the ordinary least squares values that I had come up with earlier. I tried several different neural network models, and the best one that I could come up with using NNet was 5247. Again, remember way back at the beginning of this, I was more in the low 4,000s as my best winning measurement so far. Finally, and again, this was another package that I was not very familiar with. I'd only tried once, but there's a deep learning package called H2O, and I tried using that. And ultimately, at the end of the day, that actually gave me the single best value, which was 3826, or root mean squared error of about 62. So still off by about 2 rounds, or a little bit less than 2 rounds. But that was the best that I was able to do, was 3826. Again, using the data that I had. I had somebody ask me the other day, what, if you were to do this again, what other information would you bring in? I'm certain that there are other statistics that I could, and other data that I could have added into the model that I did not really, I really didn't have access to them. So there's other statistics for, and again, this was for one position, wide receiver. But the things like hand size, how often was that player targeted by the quarterback during the season? I couldn't find access to those statistics. I'm sure that they're used by NFL scouts. I don't know where to get them from. So the conclusion, result of this analysis is less than perfect. At the end of the day, bottom line is I couldn't beat Mel Kiper and Todd McShay. But anyhow, I learned something along the way, which is what my goal was. So at the end of the day, results less than perfect. Best model is on average wrong by roughly 2 full draft rounds on average. But nevertheless, it's not. It still provides some value. It's not hugely off. It's not that it doesn't know at all. It does provide some. There is a relationship that is built. It can be improved with more and better predictors or time. But along the way, what I learned was multiple machine learning methods, including deep learning, which I really only played with a little bit before. Some more R programming skills. Again, not a programmer, but I learned some along the way. Some proper statistical test usage back in the first section, and a little bit more about the NFL draft. So those were the learnings from my point of view. If we go back over here, some of the things that I did learn, R Markdown. That document that I just showed you was put together with R Markdown. That's the first time I ever used R Markdown. So that's another thing that I ended up learning. on top of, like I said, multiple algorithms, programming and building functions. I am no expert at building functions. At the end of the day, there's a couple other learnings. No statistically significant bias toward any individual player position. And then again, the winning algorithm was with using the H2O model with a root mean squared error, an average variance of about 62 picks. So at the end of the day, I need more data and more attributes and a little more training in order to beat Mel Kiper and Todd McShay, but I thought it was a good start. And that's it.
How far off were you? I mean, Mel Kiper and Todd.